Good afternoon, and welcome to the technical overview of Windows NT. I'm Peter Weiss, a software consultant working in Digital's General International area. I prepared today's material to help both customers and employees gain a better understanding of how Windows NT is organized. Today's presentation will provide more technical detail than yesterday's Management Overview DVN. We will be looking at all the major components of the Windows NT operating system, starting from the user environment and moving down into the lower levels of the executive and kernel. Keep in mind, however, that with just a few hours available, I will only be able to provide an overview. But for those of you who leave this course hungry for even more details about the internals of Windows NT, there are additional sources of information available to you. An excellent place to start is the Microsoft Press book Inside Windows NT, which provides a very detailed yet very readable look at the design of the new operating system. You can order Inside Windows NT from Microsoft Press. The cost is $24.95, and you can call them up to order it at 1-800-MSPRESS. In addition, a follow-on course to Windows NT Awareness called Windows NT Technical Planning also takes a deeper look at various NT operating system components. That course is currently being piloted and should be available very soon. And again, you can look at that under Microsoft Windows NT Technical Planning. The course number you can look it up under is EY L5580. Finally, several notes conferences are available on the network to people seeking more information on Windows NT. They include the following. For the people who are interested in just general information about Windows NT, such as where we're going as a company with Windows NT, if you have marketing questions, if you're concerned with the types of applications that are being ported over to Windows NT. The conference you really want to look at is under DECWET, D-E-C-W-E-T, Windows NT. The next conference, DECWET, NT Developers, is more focused on people who are either installing the Windows NT software or are developing applications for NT. And in here you could find questions about what type of hardware is supported under the latest version of the Windows NT Beta Kit. Or if you have installed the software and you have problems booting it up, that question could probably be asked in NT Developers. And also, again, if you're developing applications and you want to know how to use some of the system services, there are some excellent NT engineers who are monitoring that conference. And finally, for those of you anxious to learn more about the PathWorks for Windows NT product, there's a notes conference specifically devoted to that. It can be found on LJOHub:/PWNT. Now let's take a look at the agenda for today's technical overview. We're going to start out by reviewing just a couple of slides from yesterday, especially for those of you who may not have attended the management overview. After that, I'm going to look at a couple of other operating systems prior to looking at NT. And the reason for that is just so that you have something to compare NT to. Then we'll start going through the Windows NT system architecture, starting from the upper levels, the environmental subsystems, which allow people to run DOS and various Windows applications. Then we'll move down into the NT executive, which helps implement all of the system services that applications use. We'll look at the executive, and we'll look at the kernel. Finally, we'll look at the Windows Open System Architecture. We'll look at how internationalization is achieved through the use of Unicode. Let's just review again what Windows NT is. First of all, the NT stands for New Technology. And especially for people who are moving from PCs, it truly is a new technology. It's a platform for high-end computing needs, and it's already being compared to a lot of the high-end operating systems available today. What's a little bit different about Windows NT when you compare it with other operating systems is the fact that it was built around a graphical user interface right from the very beginning. Another thing about Windows NT, which really distinguishes it, I think, from, well, especially from DOS and Windows today, is that it's designed to be portable, to be able to run on multiple hardware platforms. And yesterday we talked about how it will run on Intel platforms. It will also run on the MIPS 4000 architecture. And most of probably the greatest interest for digital is the fact that it will also run on our Alpha AXP architecture. It also incorporates many modern operating system features. And a little later on, when we go through our analysis of some of the other operating systems out there today, I think you'll see how NT borrows a lot of those features. And for those of you who are seeing NT for the first time, you may say to yourself, this looks just like another version of Windows. It looks just like Windows 3.1. The important thing to keep in mind is that, yes, the user interface looks exactly like Windows 3.1 does today. But unlike Windows, Windows NT is not layered on top of DOS. So on the surface, they're very similar. Down below, they're quite different. We said yesterday as well that Microsoft's main strategy is to get Windows everywhere. They'd like to see people using PCs, running Windows on everything from handheld computers up to the majority of the desktops and right into the large server class of machines. If we look at the strategy right now, Windows NT is being positioned for high-end workstations and servers, whereas DOS and Windows is being targeted more at the mainstream, the desktop and the portable systems. The reason for that is MS-DOS in Windows is 16-bit, which makes it smaller, makes it simpler, makes it so small and simple, in fact, that they've now been able to get DOS and very soon Windows right onto a chip, which will be very suitable for things like handheld computers and computers that will soon be coming embedded in things like TV sets. NT, on the other hand, is a 32-bit operating system, which makes it quite a bit larger, as we talked about yesterday, especially in terms of the amount of memory that's required and disk space that's required, but it's also a lot more powerful. It's a secure environment. You have to log in. You have to have a username and password. It's a multi-processor operating system, so it's going to scale up very nicely to very high-end multi-processor systems. It's portable, the hardware portability again. And it has a huge capacity, especially with that 32-bit addressing, in terms of the amount of memory and the size of the disk files which it can accommodate. And again, as we said yesterday, it's really the next logical step for the PC world. It brings most of the modern operating system features to the Windows platform. And some of those features include the preemptive multitasking, where different tasks can run simultaneously and some can have higher priorities than other tasks. We talked about the multi-threading, which is the ability to separate a process. A process is basically an application which is running into several subunits of operation. And we'll talk more about multi-threading in a little while. It allows for virtual memory so that now applications can address much more memory than is physically available on the system. You have networking built into the Windows NT operating system. And right from the beginning, you have support for LAN manager protocols such as TCP/IP and NetBEUI. You've got the support for volume shadowing so that you have a lot of fault tolerance, especially in the way that disks are handled. And again, you've got the security built in, and we'll be talking today about how that security is actually implemented by the Windows NT operating system. Let's start out by looking at the DOS operating system. And as I go through describing this, you may want to look ahead to the next slide yourself out there in the audience, because a lot of the things I'll be covering are detailed on that next page. Under DOS, you've got what I would almost call a monolithic operating system, in that the operating system itself is comprised of a number of different procedures which are really piled on top of one another in no very consistent pattern, so that you have one procedure calling another procedure, again, in no particular order. Some other things about the architecture is the fact that applications have direct access to hardware resources. And in fact, under DOS, an application can directly access a physical sector on a disk drive or a particular location in physical memory. And what that means from a user standpoint is that applications are very powerful, but they're also very dangerous. So that if you have a particular application which does something which isn't correct or isn't suited for that particular system, there's a good likelihood that that whole application, and therefore the whole operating system, may actually crash. So if we just review for a second some of the characteristics of DOS, it consists of a set of procedure. Any procedure can call any other procedure, and there's no data hiding. Now, in terms of being able to upgrade DOS and add new features, that sort of hodgepodge organization of the features means that it's very difficult at times to upgrade the operating system. Because if you modify procedure XYZ, that may also affect procedure A, B, and C. And that can, of course, be a problem as you're going. Another issue is that because applications can directly access very critical system resources, you're often switching between kernel mode and user mode. Kernel mode is the mode that an operating system runs in when it does go after and does access those critical resources. User mode is what an application is running in when it's not. The second operating system that I'd like to look at is, or operating systems, is really VMS and Unix. And I'm sure that some of you people out there who are devoted to VMS are sort of cringing when you see Unix displayed on the same slide, and same thing perhaps with some of you Unix people. But I think that both of the operating systems, in fact, do have some similarities. I would call them a layered operating system, in that the operating system consists of different layers of services. And the ones that you see in your picture up at the higher levels are more generic system services. And because they're more generic, they're also less powerful. They're not capable of directly accessing the hardware. Then when you go down through that picture, the lower you get, the more powerful the services become. And it's typically only engineers who are working on the operating system itself that are able to go in and make use in their programs of those lower levels and to modify those lower levels. Now, what this means from a maintainability standpoint is that if I want to go in and add some new features to VMS or Unix, what I can do is I can either swap out one of the layers and substitute a new version, or perhaps I'm going to add another layer. For example, I may want to add a new type of file system. And what I can do is basically insert a new layer and have that new operating system supported. Well, this is a really nice feature, and it's served very well for both VMS and Unix. One of the problems of this layered approach, however, is that you can start adding more and more and more and more features, and the operating system ends up getting bigger and bigger and bigger, requiring more memory, more management of all those resources, more disk space. It takes longer to boot up and longer to recover from crashes. So there are some shortcomings to this particular architecture as well. Let's just take a moment to review, again, some of the characteristics of what I would call these layered operating systems. Again, they're divided into modules of system services. The code at any layer only calls the code directly below it, so that you really do limit the amount of all-powerful code. Especially the types of all-powerful code that an ordinary application programmer can write. And enhancements to the operating system are a lot easier because you're able to either remove a layer and add a new version, or you can simply add an extra layer on top. The next operating system I want to look at is the Mach operating system, which is the basis for other operating systems such as OSF1, the Next Step operating system by NeXT computers, and is also, I think, the basis for a lot of what Windows NT does. Mach, in case you're not familiar with it, was developed at Carnegie Mellon University. And the goal of the programmers there was to try to simplify the actual operating system itself and to rewrite it in much more of a client-server fashion. So under the Mach operating system, what you have is something called a microkernel, which is basically your operating system stripped of a lot of its features. And a lot of those features instead are re-implemented as user mode applications. These applications happen to be servers which provide a particular type of service. So if you look at the picture, you have servers responsible for managing or providing the creation and termination of processes, in charge of allocating and managing memory, doing graphics, display, file I/O, and so on. Your application that you're running acts as a kind of a client which makes a request to the operating system in the form of a system service. That request then gets passed to the particular server, and it's up to the kernel to figure out which server to call. The server then goes out and does whatever you ask it to do and returns some sort of a value, so it returns a reply. Now, a server could also be a client. For example, let's take the case where I want to go out and not access a file on the local system, but a file somewhere else on the network. I might have my application, again, make a file service request. So the kernel would take that service request, pass it to the file server. The file server would look at it and say, aha, a remote system has been specified. So let's take that and pass that to the network server. And from there, the network server would make the appropriate calls to get it from that remote system. So you can see that a server is not just a server, it can also be a client. Some other things about the design of the Mach operating system. Because you've removed a lot of the applications, or I'm sorry, a lot of the operating system functions away from the kernel itself, the kernel is much smaller, it's much more easy to maintain, and because it's so small, it tends to be a lot more portable. And in fact, that's one of the features they were looking at in the design of Mach, was to make it as portable as possible. And certainly one way to do that is to make it small. Another thing about Mach is that it is much easier to upgrade the system. For example, to add a new feature, again, such as a new file system, what you can do is write a new file server, or perhaps a new memory manager. And in fact, if one of these servers happens to die, it's possible that you could keep the operating system running and simply restart that server again. So let's, again, review some of the things that I've talked about with Mach. The Mach operating system really is a client-server OS. It's divided into several processes which run in user mode. Now, because of each of these are running in user mode, it means that it's, again, if one of them crashes, it's not necessarily going to bring down the rest of the system. Also, each of these processes really implements a single set of services, so it makes things much simpler and much more modular. Some other things about Mach and OSF1 and the other systems which are based on Mach. A client can be an application, or it can be another operating system component. They're fairly self-contained. And one thing that I didn't mention earlier was the fact that this type of operating system design is excellent for multiprocessing systems, because each of those servers, since they're nothing more than an application really, can run on several different processors. And you can get an excellent increase in performance as you start adding new processors to that system. Okay, now let's take a look at the Windows NT architecture. The first illustration we're looking at here is somewhat simplified, and we'll be looking at a much more complex diagram a little later on. But Windows NT, as we said earlier, allows you to run a variety of different operating system environments. You can run applications that were written for DOS, for Windows 16 bits, for Windows NT, OS2, and POSIX. And what happens is you start up an application. Another application called the single command shell figures out what type of application that is, whether it's DOS or Windows, etc. And then the executive looks at that, calls the correct subsystem, or the correct environmental subsystem, which then handles that. And it's really a lot like Mach in the sense that you've got applications calling into the executive or the kernel, and then having a lot of the requests passed back out to one of the servers. And each of those environmental subsystems is really a separate server process. And in a demonstration a little later on today, we'll take a look at how you can view each of those servers running. we'll also see in a second when we look at a more complex diagram of Windows NT is that it's not quite as much of a client-server environment as Mach is. They've moved some things back into the executive in order to get a slightly greater increase in efficiency. The purposes of this type of client-server model that we're looking at with Windows NT is, again, like Mach in that you're simplifying the base operating system. What you're removing out of the operating system is the handling of all the different families of APIs which are supported, such as DOS, Windows 16, and so forth. The goal is to make, again, make the operating system simpler, but also to make it easier to add new APIs. For example, some people have suggested in the future, wouldn't it be great if we had a VMS subsystem running on Windows NT which could handle VMS applications? Well, perhaps sometime in the future there will be a VMS subsystem. I don't know anything that's being planned in that area, I might add. The other thing about this type of environment, again, you're improving reliability because every server is running as a separate process. So, for example, you go and you run your MS-DOS game, and it's not particularly configured for that system that you have. The DOS application crashes. However, only the DOS subsystem will crash, not the entire operating system. So you've got an increased reliability because you don't have that type of thing where a poorly written application can bring down the whole system. And then the other thing about this model, again, is that it really lends itself to distributed computing in that the applications themselves are designed using a client-server type of a system. They use a technique called local procedure calls to pass messages back and forth between one application and another. As we'll see, local procedure calls are really nothing more than an enhanced, optimized version of remote procedure calls. So it really does fit in nicely to the distributed client-server model that Microsoft is looking at for NT. Okay, here we have I guess the full-fledged picture of the Windows NT architecture, showing up at the top all of your environmental subsystems as well as down below the parts of your executive. Let me go over to the monitor for a second and just, again, point out some of these things. Up here at the top, we have our applications that we would be running. These would be written using a particular set of APIs, again, a DOS API, a POSIX API, or so forth. Those applications are then handled by the appropriate subsystem, such as the OS/2, the POSIX, the Windows 32. Something which I don't have in this diagram, which you may want to add to your illustration, is right in this area here. As we discussed earlier, and I'll also be talking about later, there's a special application called the Virtual DOS Machine, or VDM, which handles all of the requests for 16-bit and DOS applications. Actually, just one correction to my illustration. It shouldn't really go into Windows 32. It's specifically for Windows 16 and DOS. So what we're going to do in our discussion of the operating system is to first look at the upper-level subsystems. Once we're done with that, I'm going to give you a demonstration of that. And then we're going to move down into the lower-level sets of managers or subsystems, sometimes called the integral subsystems, which are there specifically to implement various families of system services. So again, why do we want to have these protected subsystems or environmental subsystems? Again, they implement a set of APIs. They use a special facility called local procedure calls to pass messages back and forth between a client, which could be an application, and a server, which might be something like the Windows 32 subsystem. The client could be an application. It could also be another server. In that illustration, there are two types of subsystems you have. One is the environmental. That's the subsystem which exists to handle one of the APIs you write your applications with, so Windows 32 or DOS, etc. and then you have the integral ones which perform executive functions and implement system services calls. The purpose of them is to make the system more extensible because you can add on to the operating system by simply adding additional subsystems. One thing to keep in mind when you're developing applications, however, is that you really can't mix and match these APIs. You can't mix and match the APIs. So you could not have, for example, Windows 32 calls mixed in with POSIX calls. The reason for that is the different operating system models or the different environments have different concepts of what a process is or what a thread or what a file handle happens to be. The first subsystem we're going to look at is MS-DOS. Over on the left-hand side of your illustration, you see a representation of a console. What happens when you use the Windows user interface and you click on the icon that says MS-DOS prompt is you create a console window. This console window is what's called a single command shell. And again, you will issue a command such as dir or edit, and the operating system is going to figure out which environmental subsystem to invoke. So for example, if I type in the word edit, I'm invoking the MS-DOS editor. What's going to happen at this time is that the operating system is going to create a special application called the virtual DOS machine. The job of the virtual DOS machine is to take our application and make the appropriate system calls to recreate the DOS environment. Everything from allowing the system to handle interrupts, to handle BIOS, to make it think it's sitting on a PC that's running MS-DOS. Now, a couple of things happen. All of the calls to the graphical user interface, okay, so when you type out the characters EDIT, and when you get the display of the editor on the screen, all of that graphics type of oriented stuff is handled directly by the Windows 32 subsystem, and in fact is handled in full native Windows 32-bit mode. So graphical operations are going to be fairly quick. Times when you call into the system services to do such things as the management of files, to do memory management and so forth, those are going to go through the NT executive in 16-bit mode. So those are going to be a little bit slower. Some other things about the virtual DOS machine. Every time you open up a new console window and start up a new DOS application, you have a separate virtual DOS machine. And as we saw in yesterday's demonstration, what happens when you start up that DOS machine is very much like what happens when you start up a DOS program today. You have your config.sys being executed and your autoexec.bat file being executed. And again, that's going to happen for every console window that's open. By the way, the executable that's running that handles all of those different commands, so the real single command shell application is something called cmd.exe. And again, in a demonstration we'll be showing in a little while, you'll see how cmd.exe as well as the NT virtual DOS machine relate to one another. So to recap some of the points I made with that slide, you have virtual DOS machines being created. The VDM is actually a Windows 32-based application, a very complex one. And if you go and get that book, Inside Windows NT, that I was talking about and read about it, you'll see that included in that application is MS-DOS source code, at least on the Intel platform, which is responsible for handling a lot of the DOS calls itself. Again, it creates a complete virtual computer running DOS. Applications are running in user mode, which means that even though the DOS application itself may think that it's going out and physically accessing physical hardware or software, it's not actually doing that. It's going through software itself. And again, you can have any number of VDM processes running at the same time. So in fact, by opening up separate console windows and starting separate DOS machines, in effect, you're getting a pseudo multitasking MS-DOS operating system. When you run Windows 16-bit applications, something happens which is very similar to what you get with the MS-DOS programs. When you start up your first Windows 16-bit application, either from an icon or from the command line, you again create a virtual DOS machine. There's some special things that there's some things that are special about this virtual DOS machine. It's really one specifically for handling all the Windows 16-bit programs. So there's certain other things which get started up at the same time. And for that reason, when you start up your first Windows 16-bit application, it takes about 10 seconds for the environment to get in place and to get all the various header information and data structures initialized. But again, your Windows 16-bit application goes through the virtual DOS machine. Any graphical user interface calls, so again, things like pull-down menus, pop-up dialog boxes, the handling of your keyboard and mouse input, are all going to be handled in Windows 32-bit mode. They have a term they use at Microsoft called thunking, T-H-U-N-K-I-N-G. You take 16-bit calls and thunk them into 32-bit calls, and that's exactly what's happening in this case. Again, the calls that go into the system services, so things like file I/O and memory management, are still going to be handled in 16-bit mode. Because you really have these two different ways that applications are handled, it's a little bit difficult to say specifically how applications are going to be, how 16-bit applications will perform under Windows NT. Some may perform very well if they make a lot of use of the graphical user interface. Others may operate a little bit slowly because they make more system services calls. They may do more things like internal calculations and so forth. So again, the 16-bit programs run within the address space of a virtual DOS machine. One point I didn't make before, but it sort of showed up on the diagram, was the fact that every Windows 16-bit application shares the same virtual DOS machine. So you have a single virtual DOS machine created no matter whether you have 1, 2, 3, or 100 16-bit applications running. And if you think about it, that really makes sense. Because what happens today when you start up Windows? You boot up a single DOS machine, then you start Windows by typing WIN, and all of your applications are handled through that single instantiation of Windows. Now, you may say, well, isn't that going to be a performance problem? Well, possibly it could be. But again, remember that the Windows graphical user interface calls will be handled by the 32-bit API. The term they use within Microsoft for this environment is sometimes called WOW, which is really short for Windows 16 on top of Windows 32. The next subsystem is the OS2 subsystem. One of the things you want to, there are actually a couple of things you want to remember about the OS2 subsystem. First of all, the support right now is very limited. With this subsystem, you can only run applications which were written for OS2 version 1.0, 1.1, 1.2, and so forth. You cannot run any applications which were written for OS2 version 2.0. In addition, there's no support for Presentation Manager applications. Presentation Manager is a graphical user interface that OS2 uses. Another thing is that what that means is that you have to run all of these OS2 applications from a console, much like you do with DOS. And so they're text-based applications. There may be people out there, though, that have things like server applications or editors which are OS2 programs. They're written under version 1.x, and they operate in a character cell window, so those should be fine. The other thing about the OS2 subsystem is that it will not be available on either the MIPS or the Alpha platform. One of the main reasons for that is OS2 itself was very much designed around the Intel architecture. It is written mostly in assembler language. It has a lot of assumptions built into it on what the underlying hardware platform will be. So it would have been a very difficult subsystem to move over to MIPS and Alpha anyway. And then finally, you have the POSIX subsystem. As those of you, for those of you who don't understand POSIX or are not very familiar with it, Basically, POSIX is a set of standards which were written by a variety of companies, and it specifies standard APIs for various types of applications that you might want to write. For example, there's a set of POSIX standards for general system services, such as file access, memory management, and so on. That particular standard is IEEE standard 1003.1. There are other POSIX standards for things like doing networking and for creating graphical user interfaces. The POSIX support under Windows NT is fairly limited in that it only supports that one standard, 1003.1. So you don't have the ability right now with POSIX to write graphical user interfaces for your POSIX app. They have to be character cell-based programs using a console interface. The main reason POSIX is there right now, and Microsoft even says this themselves, is because there are times when you have certain bids, when you're bidding an operating system, and typically governments, but also a lot of big industries, specify as one of the things some type of POSIX conformance. So this is kind of a checklist item which says, yes, we have POSIX conformance. However, you need to remember that a lot of the actual POSIX features that you might see under something like OpenVMS simply won't be available there. I think, though, that if some of these additional features were added, such as networking or graphical user interface, it might be a very nice API for people to use who are moving existing Unix, VMS character cell-based applications. What we're going to do now is give you a demonstration of the environmental subsystems showing you how the virtual DOS machine works. In case you missed our demonstration during the management overview, what you're looking at on the screen right now is what you see when the system is first rebooted. The welcome window asks you to press Control-Alt-Delete to log on. Now under DOS, Control-Alt-Delete would cause the system to reboot. But what it does under Windows NT is enters you into the security subsystem. From here I can type in a username, of which there are several on the system, as well as a network domain that I want to log into, and finally a password, which is the only thing I need to supply at this point. What I'll be doing during this demonstration is to show you some of the ways which virtual DOS machines get created. Now, in order to view the creation of those VDMs, we're going to start up an application which comes with the Windows 32 Software Development Kit. So allow me to open up the Software Development Kit program group. In here is an application called Process Viewer, or pview, which allows us to look at various processes that are running on the system. Now, what I'm going to do is make sure that we do not have any virtual DOS machines running right now. So I'm going to look for applications or processes called ntvdm.exe. And as we go through here, we'll see that, in fact, none exist. Before we create some, let's look at some other processes which are running, though. Here we have the OS2 subsystem. This is one of the environmental subsystems that we talked about just a little while ago. A little further down, we have the POSIX subsystem, which, as we can see down in the lower window here, is actually a multi-threaded environment using 6 separate threads. Now, in order to create the virtual DOS machines, the first thing I'm going to do is open up a single command shell window. Remember that the MS-DOS prompt, although it's named such in the icon, is actually a shell which allows you to run OS2, POSIX, Windows, or DOS applications. I've started up this prompt window. Let me go back to the process viewer for a second, refresh the display, and we'll see that up at the top is a process which wasn't there before, cmd.exes. One of these is created every time you open up a console. Now I'm going to go to the console and I'm going to type in edit, which is our MS-DOS editor. We have a config.sys file and an autoexec.bat file being executed, and now our editor appears on the screen. Let me go back to the process viewer, press the refresh button, and now notice that halfway down through the display we have NTVDM, Virtual DOS Machine, which is handling that editor application. And we can see that it's created with 3 separate threads. Let's go and create a second DOS application, because I want you to see how every DOS program has its own virtual DOS machine associated with it. I double-clicked on the MS-DOS icon. Let's go back, refresh the process viewer, and we see that we now have 2 cmd.exes up here, one for each of our consoles. I'll start up the DOS shell. And while that's starting up, let's go back, refresh the process viewer, and now we can see that we have 2 NTVDMs, a separate one for each DOS application. Now I'd like to show you what happens when we start up Windows 16-bit programs. As I said earlier, each of those 16-bit programs shares the same virtual DOS machine. So what I want to show you is that every time we start up a new Windows 16 program, we have only one virtual DOS machine getting created. I'll open up a third console and execute a 16-bit program. What I'm starting up is an application associated with the Quick C for Windows package. This particular application, QCWin, is the main application window. Because there's a lot of work which goes on in starting up the Windows 16 on Windows 32 environment, the first time I start up a 16-bit program, it takes a while to get going. It'll take about 10 seconds. The next application, the next 16-bit application, will start up much faster. So we'll start that up. In the meantime, we can go back to the process viewer, refresh it. We now have 3 cmd.exes, one for each console. And I would expect to see 3 virtual DOS machines. Again, one for the editor, one for the DOS shell, and one for the 16-bit Quick C for Windows. And there it is appearing on the screen. Finally, let's create one last DOS window. And again, to quickly jump back to the process viewer, refresh the display, and we see that we now have 4 consoles. I'll start up a second 16-bit program. Starts up very quickly because we've already initialized Windows 16 on Windows 32. And finally, let's look at this display one last time. We see that we have 4 cmd.exes, one for each console that we've opened up. But we only have 3 virtual DOS machines, one for the DOS editor, one for the DOS shell, and one which is shared by all 16-bit applications which are running, 16-bit Windows applications. That concludes our demonstration of the virtual DOS machines and the Windows NT environmental subsystems. While we're waiting for some calls, I'd just like to review some of the characteristics of the operating system, especially the environmental subsystems. Some people have asked, what is the performance of the DOS subsystem going to be? And it's really one of the things that Microsoft is working on enhancing as much as possible. They realize that with some of the early beta versions, the performance isn't quite up to what they expect. Based on my personal experience, I've been very pleasantly surprised with the Windows 16-bit environment especially. I've had situations where certain applications that I can't get to run under Windows 3.1 actually do run under Windows NT. Uh, okay, we have a call from New York. Hello.
Hi there. I'm wondering if the procedure call metaphor that you mentioned earlier means that all the procedure calls that can be executed locally can be executed remotely, and that NT is providing some sort of transparency for this?
Okay. Talking about local procedure calls versus, say, remote procedure calls. Right now, the local procedure calls are actually a highly optimized version of remote procedure calls. However, the local procedure call API is not exposed to developers at this time, contrary to what I have in a slide coming up. What happens, though, is that if you execute RPC calls on a local machine, in most cases, those RPC calls will automatically get converted into LPC calls and be executed that way through that more highly optimized mechanism. So I think that in terms of designing applications, if you can try to design them as client-server applications using RPC, and we can, I think, say that in many cases it will use LPC if you do run it on a local machine. Does that answer your question?
Sure. Just to summarize my understanding of it, that means that we're still in a mode where an application needs to be written from the beginning, understanding whether it's going to be a local application or a client-server application. Because
Right.
the two APIs would be different.
Exactly. Yes. There's no way to kind of magically make that happen or make that happen in any easier a fashion than it does in today's environment. Correct.
Okay. Thank you very much.
You're welcome. Okay. We have a call from Merrimack.
Hi. I'd like to know what the minimum amount of physical memory is required for creating a virtual DOS machine process.
Okay. That's a very good question. Let me just ask you this. You want to know just how much memory is being taken up by the virtual DOS machine itself?
Well, I guess there's two parts. One is to execute the virtual DOS machine process, and the second one is to bring in the application.
Okay. I'm afraid I don't have any hard figures for you on that. However, using the application that I was showing you before during the demonstration, the process viewer, you can use that to take a look at the amount of memory being consumed by every application. I don't believe in that demonstration I showed you that feature, but that is possible. And I think that would give you some hard data on which to measure that, but I'm afraid I haven't done that myself.
Okay, my next question is related to this. If you don't have enough memory left to create a new process, do you get appropriate error messaging?
Well, in terms of not having enough memory available, remember that Windows NT is a virtual memory system. So as what will happen is other processes will be paged out, or certain parts of the virtual DOS machine will be paged out as required if you don't have that amount of physical memory available. So I don't think you'll actually be running out of memory in the same way that you would under DOS today. Does that answer your question?
I guess so. You could probably hang in that case, right?
You could probably hang?
Or it would be perceived as a hang because it would be performing so slowly?
I suppose it's possible. Again, I haven't seen any cases where that has happened, though.
Okay, thank you very much.
You're welcome. Okay, hello, New York. You have a question, New York?
Yes, this is Albany, New York. In watching your demos yesterday and today, the performance seems outstanding on the machine you're using. I wonder if you could just tell us about the configuration that you're using there and the type of, looks like a laptop or a portable that you have.
Sure. It's a Toshiba 6400 laptop. I wouldn't call it a portable so much, having carried it pretty much around the world, but it's a nice system. It's based on a 48633DX chip. It's got 200 megabytes of memory. I'm sorry, 200 megabytes of disk space and 12 megabytes of memory.
Oh, very good. Thanks. It's good to see that kind of performance from that configuration.
Yes. I hope that in the future sometimes Digital has a similar machine configured in that way.
Great. Me too. Thanks.
Okay. Okay, we have a question from West Texas. Hello. Oh, I'm sorry, Dallas, Texas.
Hello.
Hello.
Question is, on the DOS shell and the editor, why are those not treated like 16-bit applications?
They're not treated like 16-bit applications. Well, in a sense they are. They're not being treated like 16-bit Windows applications because these are character cell-based DOS services that under DOS would typically run in a non-Windows environment, although they could also run in a console application within Windows. Does that answer your question?
So in other words, the VDMs, the copies of VDM, are only needed whenever you have console applications, multiple copies, that is.
That's right. Well, yes and no, in that, that's true for DOS applications, such as the editor or such as the DOS shell application, or perhaps a DOS game that you're running in a console window. But again, all Windows applications written using the Windows 16-bit API will share the same virtual DOS machine, whether they're started up from the same console window or different console windows or even from icons.
Thank you.
You're welcome. Parsippany, hello.
Yes, I wanted to understand fundamentally what was the difference between Windows NT and X Windows, and when would you choose to steer a customer towards Windows NT or an X Windows based front end?
Okay. Good question. The question being, if you didn't hear it, what are some of the fundamental differences between the X Windows system and Windows NT? One of the differences, I think, is that, again, Windows NT, that user interface is a key part of the operating system, whereas the X Windows system has really been layered on top of VMS and a variety of Unixes. Another key part is that the X Windows system is a client-server-based windowing system in that your user interface code is created by the X library or by the Motif toolkit. That application that you're running is the client. The workstation that you're displaying the user interface on is a server, in that it's typically called a display server, because it can handle various requests from various other systems to display graphical user interface elements. Windows, on the other hand, is not distributed in that fashion, in that you cannot take an application and run it on one PC under NT and have the graphical output display on another system also running Windows NT. That's probably the basic difference between the two. Welcome back. Before the break, we took a look at, I'd say, one half of the operating system. We looked at the environmental subsystems that you see pictured on this chart. We talked about OS/2, POSIX, Windows 32, and the DOS subsystem. One we didn't have a chance to cover yet is the security subsystem, and we'll take a look at that a little bit later on. What we're going to do now is move down into the lower levels of the operating system, starting with the executive. It's the job of the executive, through the use of the integral subsystems, such as the memory manager, the process manager, and so forth, to implement various classes of system services. After we look at those integral subsystems, we'll then take a look at the kernel as well as the hardware abstraction layer. The first component I'd like to look at is the Windows NT Object Manager. NT uses an object-oriented approach to manage various families of resources. Some of these resources are hardware resources, such as I/O devices, physical memory, CPUs, and so forth. You also have software resources, such as files, security issues, processes, and semaphores. All system data that's going to be accessed by user mode applications is defined in an object. For those of you who aren't too familiar with object-oriented methodology, objects tend to consist of two things. It consists of a collection of data, typically represented by a data structure, as well as a set of functions or methods which are used to modify that data. And as we'll see, Windows NT uses both of these. Perhaps some of you who have been keeping up with Microsoft in the press have heard about another future version of Windows NT called Cairo. What Cairo is going to do is it's going to bring object orientation up to the user interface. And people will be able to manipulate all types of different data, whether it be textual data, graphical data, perhaps video clips, in a uniform manner so that they don't have to really worry about what data type they're dealing with. Windows NT today doesn't do that. And I think what Microsoft is really doing is getting some experience with the object-oriented approach, implementing it at a more transparent operating system level, and then they'll be bringing it more to the user interface level in future releases of NT, such as Cairo. The Object Manager, again, takes a benefit of an object-oriented approach. With object orientation, you can do things like use the same, take advantage of similarities between resources. When you think about it, dealing with files and dealing with memory are done in a very similar fashion. Each of them has some location. They each have some size. You can read to memory or to a file. You can, read from it. You can write to it. You can delete it. And so the object-oriented approach allows you to have similar code, which is really independent of what the actual type of data you're dealing with is. So what this means is you can use common code to manage similar objects. Let's give some examples of that. And you may want to think of, for example, a spreadsheet. When a user starts up any type of application, in this case we'll say a spreadsheet application, the Windows 32 subsystem is going to create several things. It's going to create a process object, and it's also going to create a thread object. Because under Windows NT, every application creates a process, and that process has to include at least one thread. So what's going to happen is a system service call called createProcess will be called by the application or by the operating system. The process manager, which we'll get to in a second, will then send a signal to the object manager saying, create me a process object. And then the object manager will go and pass a handle to that process object or an identifier to that process object back to that process manager. In the same way, if a user has gone in and written to that spreadsheet and entered some new data, they now want to go store it, what's going to happen? Well, there's going to be a system call to something like open file. The Windows 32 subsystem is going to call into that I/O service, make the call to open file, and the I/O manager will again make a call to the object manager saying, oh, I've got to open up a file, so you, Mr. Object Manager, have to create a file object in which we'll identify again the file, the length of it, security data, as well as a lot of other critical information. You can see in this diagram, again, how those various integral subsystems call the object manager during various activities on the system. Just to give you an example of how one of these objects might be organized, let's go back to the process for a second. You would, again, every time you create an application, you'd create a process object. The process object, first of all, consists of various attributes. Those attributes include things like the process ID. Every application which is running has its own unique process ID. It's going to contain information on the priority of that process. So basically, it's base priority level. You'll have the execution time and the exit status of that process. So those are all attributes or fields within a data structure, if you want to think in more conventional terms. And then the object manager also helps the system implement the various types of service. So defined within that process object, again, are various system services such as create process, terminate process, read or write to the virtual memory, and various other things that processes have to do in the course of running. And the same thing would apply to such things as a file object. So to, again, go over some of the, review some of this, the job of the object manager is to basically identify and catalog the names of all of the different NT resources. It's also responsible for keeping track of the means to access these resources. In other words, what are the services which an application can invoke to go in and modify a particular object. It maintains all of the data that's associated with those resources. And that data is constantly being modified by applications as they call the various system service routines. And perhaps as important as any of these is the object manager is responsible for tracking the authorization permission of each of the types of objects which is created. And within the Windows NT security system, you can have access control lists not just to files, but also to various other processes and so forth that you're using on the system. One last point about the object manager is that there are actually two types of objects which the operating system creates. The first one is an executive object. These are the objects which are modified by applications that are running in user mode. So these are the things that we've talked about, such as processes, files, security objects, and so forth. The other class of objects are kernel objects. These are used by the operating system itself. The process manager is the second subsystem. The process manager is, as its name might imply, responsible for creating and terminating various processes and threads. It's up to the process manager basically to provide those set of services that the environmental subsystems need. And if you go in and look at that book Inside Windows NT, they talk about in there about how they design the process manager to be as generic as possible so that it can be used by all of the different environmental subsystems, such as DOS and Windows 16 and POSIX, which each happen to have a different concept of what processes and threads happens to be. But the process manager is flexible enough so that it can handle all of those. The other job of the process manager is to suspend and resume the execution of threads. So remember again that a thread, first of all, let's go back to a process. A process is really a job that the operating system has to do. It's a task that has to be performed. And you can think of a thread as a subtask, and which may be one of many subtasks or one of many threads which is part of that job or that process that has to be completed. So again, the process manager manages both the processes and the threads. The process manager is also responsible for storing and retrieving information about your processes and threads. And it does this by communicating, again, with the object manager. One thing that's a little bit unique about processes under Windows NT is that there's no parent and child relationship between one process and another. So that in fact, which is what you do have in something like a VMS or a Unix system where you have this parent-child relation. And if the parent is terminated, typically the child application is terminated as well. That is not the case under Windows NT. Every process is its own unique identity. A key component of the underlying executive is the local procedure call facility, which I talked about before. It's responsible, again, for passing information back and forth between client processes and server processes, typically on the same computer. Now, these processes might be, again, applications, or they might be other servers as well. The actual passing of the information can be done in several ways by the LPC. It can use shared memory, or it can use a message passing mechanism. As I indicated earlier, local procedure calls are really nothing more than a very flexible and a very optimized version of remote procedure calls. the design of LPCs is very similar to remote procedure calls. The last item you see here is one that I have to correct. Local procedure calls at this point are not actually exposed to application developers. What you would have to do is you would have to use remote procedure calls to develop a client-server application that way. And then if you run each component of that client-server application on the same machine, the operating system will figure that out and use local procedure calls as the message, as the communications path there, and you will get very good performance. This picture shows, in at least brief outlines, how local procedure calls work in general. You have your client process, which again may just be a standard application, or it could conceivably be another server. And what that's going to do is it's going to send a request to a particular, a request to connect to a server process. Now, a server process is going to have a communication port open at all times, listening for requests for that service. When the request comes in, the server is going to look at its own internal data structures and determine, number one, do I have enough resources to be able to handle this new request for a service? It's also going to check with a security subsystem to make sure that that client process has the permission to access that server. When all of that checking is complete, then you're going to have yet another communication port opening up on the server. You're also going to have one opening up on the client, and then information gets passed back and forth between them. This illustration is very similar to what you would see in a similar discussion on remote procedure calls. And again, the two of them are very similar. I feel that the whole local procedure call and remote procedure call capabilities open up a lot of interesting possibilities to create very flexible applications. Let me go over to the whiteboard for a second and just give you a possible scenario. Let's say that I was designing an application which did a couple of things. We're going to have it read a large amount of data from a file. Perhaps it'll be a large matrix of numbers. We want to then take those numbers and recalculate them in some fashion. And then finally, we want to display them in a graphical way on a workstation or a PC screen. If you were writing a typical application, you would basically have a main procedure which would consist of a number of procedure calls. If you were going to try to be modular in a traditional programming environment, let's say in a C program, you might have several C modules. You might have a main.c to do the basic application startup, as well as perhaps the reading of the data from the data from a file. You might have a second procedure called calculate.c. Calculate.c. And this is going to take those numbers and it's going to recalculate them, perhaps based on some algorithms that you've got stored within that program. And then you might have a third module called visual.c. So you've got all of these created into separate files, but you would compile and link them together, and the net result would be, we'll just call it program.exe, which you would then run. Okay, nothing too unusual about that. Let's look at how you might do the same thing using either RPC or LPC. What I might do is create an application, and I'll just call it the main client. And again, its job is to go out and read some data off a disk. This is a disk drive right here. We're then going to go and create another application, and we'll call this the calculate server. And what we would do is we would use remote procedure calls to have the main application pass the data back to the calculate server, perform the calculations, and then pass that back to the client which made the request. And then finally, we'll create a visual server. And again, use remote procedure calls to pass that recalculated data down to the visualization server to actually display it on the screen using perhaps some 3D graphics package that we want to incorporate. What happens, some of the benefits of this, again, are that if you're using remote procedure calls for all of this communicating back and forth, each of these servers can be put onto a different system. So you have a distributed application. This can even be very good on a single system, because each of these servers, again, or each of these applications, which are really separate processes, get their own time slice on the CPU. So they're going to run much faster that way, because each of these processes will be scheduled separately. So other applications won't get as much processing time. But I think there's a lot more to it than that. For example, if I decide that I come up with some new algorithms for my server, what I could do is get rid of this old calculate server, bring in a new one, and not have to rewrite the other main components of my application. In fact, these might still be running on my system. In addition, I might create some new application. We'll just call it main2 client, which could also make use of these servers. And again, you write it using remote procedure calls, but even on the local system, it's going to work very well because it's going to be converted automatically by the system into the local procedure calls. So again, this is one possible scenario, and I'm sure a lot of you can think of other examples of how this type of facility might be useful. The next component I want to talk about is the virtual memory manager. As you might gather from the name, the job of the virtual memory manager is to implement virtual memory. Under Windows NT, there's actually the capability with the 32-bit addressing to address up to 4 gigabytes of memory. However, 2 gigabytes is reserved for use by the operating system. So applications themselves have up to 2 gigabytes of private address space available for each process. Now, of course, at least for the next couple of years, you're probably not going to have 2 gigabytes of memory on your system. So what it's going to do is use a virtual memory system much like VMS or Unix does, where those pages of an application which are needed at that time are going to be paged into the physical memory, and those pages which are not needed get paged out to a page file on the system. And that's one of the big reasons why when you install Windows NT, you have to create a page file that's at least 20 megabytes in size. The other thing about the virtual memory manager is, of course, that it's responsible for protecting each process's address space. So that, again, you don't have the danger like you do under DOS, where one application can write into the address space of another application. And what's more is, when you're dealing with Windows 32-bit applications, at least, you're no longer going to have to fool around with memory managers like you do today with DOS and Windows 16. So all of that will be behind you as you move into the 32-bit programs. The next component is a security reference monitor. Again, it's an integral subsystem. It's responsible for enforcing the security on the local computer. We say the local computer because with products like the Windows NT Advanced Server, a lot of the network security is actually handled by the networking software rather than the security reference monitor, although the two do work together. The purpose of it is to guard the operating system resources against unauthorized access. From the user standpoint, of course, this includes being able to log into the system or not. From there, though, you can also allow users to do certain things or not do certain things. For example, you can set up your system so that certain users can only log in and do system backups. You can have certain users who can't shut the system down, provided, of course, that you don't let them near the on-off switch as well. and a variety of other rights or privileges which can be assigned or taken away. And during the next demonstration, where I'll show you some of the system administration tools, you'll see how you can set those rights and privileges on. The other thing that it does is it works very closely with the object manager. Basically what happens is every resource or every object on the system has its own access control list, and the user who's logging onto the system also has a security object that's associated with him or her. Let's look at how the security reference monitor works. We start out with somebody logging in through the login window. Provided that was successful, provided they type in a username and a password, that name and password information is going to be passed to the security reference monitor, which is one of the executive subsystems. That then gets checked with a security database on the system. One of the things that I haven't talked about yet is that there's a database on the system called the registry, and it's within that registry that the user's security profile is sitting. So anyway, provided that the username and password are okay, then you get what's called an access token created. And this is probably a good example of what an object would look like, at least the data fields within that object. So that user is going to have information such as a unique security ID. Again, very similar to VMS or a Unix. You might have that user being a member of certain groups. When a user is a member of a group, he has certain privileges that are associated with him or her. Other types of information include what's the default access control list, which will be created for every file and directory that user creates. In other words, a user creates a file, there will be default read, write, and execute permissions set up there. So again, it's up to the security reference monitor to keep track of all of this information, and this user access token gets double-checked with every different type of resource that user is trying to access. Okay, then the last major component of the operating system, or the last integral subsystem that we're going to look at, is the I/O system. One of the main characteristics of that I/O system is that Windows NT does support multiple file systems. The first of these is NTFS, simply short for the NT file system. It's designed to be high performance. This is the file system which will give you the quickest file system I/O. You've got within this file system the logging of file system metadata. In other words, as users are moving files around, creating new files, there are different file system pointers that are being changed and modified during all this time. All of these changes are logged so that if the system were to crash, the file system pointers can be recovered fairly quickly at boot up time, so that the system can come up literally in a matter of seconds rather than minutes or hours, which it takes other operating systems to recover their file system data. So you no longer have the specter of a long file system check, such as what you'd see under Unix. Another characteristic of NTFS is that it supports very large files. In fact, 2 to the 64th power, which is something like a file that would be 17 billion gigabytes long. And that should be plenty for everyone. I forget how many zeros that is exactly. You may say, why such a ridiculously large number? Well, the next smallest size really is 2 to the 32nd power, which is only about 4 gigabytes. And there are already databases out there which are starting to exceed that size. So I think this will give the NT file system quite a bit of room for growth. The other characteristic of the NT file system is that it's the file system which actually implements the access control lists on files and directories. I may have created a bit of a misconception earlier because I kept referring to security on file systems and directories. And in fact, you don't get that security when you work with the other file systems. Those other file systems include FAT, short for File Allocation Table. This again is used by the MS-DOS operating system and is basically for that compatibility. As people were indicating or questioning about earlier on, if you want to be able to run both or boot up under either DOS or under Windows NT, you need to have a FAT file system partition as your primary partition so that DOS can find that. If you only want to run Windows NT, then you can either use a FAT file system or an NT file system. The third file system is HPFS, which is short for High Performance File System. And this is useful for OS/2 compatibility. Again, like the FAT file system, it doesn't have the access control list which NTFS offers. And despite that name, High Performance File System, it's really the NT file system which is going to give you the best performance. Another thing to keep in mind is that Windows NT includes hooks within it for adding other file systems in the future. Just as examples, not that they're here yet, people may want to add at some point the Andrews file system or the NFS file system, which actually Sun has already done with their PC NFS product. People have suggested, well, gee, in the future, maybe we should have support for something like RMS or a file system specifically tuned for transaction processing. Again, it'll be up to the market to decide, I think, whether those get developed. It's certainly not a constraint of the operating system itself. Okay, let's look at the I/O, some other characteristics of the I/O system in NTFS. Some of those, the compatibilities, as I mentioned before, is the file system logging. This isn't any sort of real magic. In other words, if you're working on a file and you've just written it from scratch and somebody shuts your system down, you're still going to lose that file data. What it's keeping track of is really file system pointers, not the file data itself. And what it does is it's basically a transaction processing type of a system or a journaling system, where as you start moving files around or modifying the pointers, there's a transaction which is open, and if for some reason the system goes down, that transaction is rolled back to the initial starting point when the system is booted back again. So there's a logging which is taking place actively as you're working. Another characteristic of NTFS is, again, that ability to handle fantastic amounts, fantastically large files. We have the security features we talked about, and we'll be demonstrating how that security can be set up under Windows NT during the next demonstration. But one of the things that people have been asking for a long time under DOS is such things as execute-only file names. So that, for example, people will be able to execute batch files, but not necessarily read the contents of them. Another thing about Windows NT is it supports, or the NT file system, is that it supports Unicode. We haven't talked about Unicode yet. We will. But Unicode allows you to do such things as have various languages included in the same file. So, for example, you could have, in a single text file, ANSI codes, English characters. You could have Russian characters and Japanese characters, all in the same file. And through use of some of the display facilities, be able to display all of those. We'll also see that Windows NT as a whole uses Unicode throughout the operating system. Talking about NTFS in particular again, it also has support for POSIX. If you're not that familiar with POSIX, you can also equate it with Unix. Both POSIX and Unix have such features as hard links. A hard link is where you have more than one file name pointing to the same collection of data or the same file data. You also have support for case-sensitive names. So you can use combinations of upper and lower case letters to have different files with the same actual letters in them in the same directory. And there's also information on when the file or the directory was modified. Now, one of the things which is not part of the NTFS file system, which a lot of people ask about, is versioning. In other words, VMS supports the ability to have multiple versions of the same file. That's not there. But again, going back to the extensibility of Windows NT, there are hooks within the operating system so that if a third party wanted to, they could add that versioning capability fairly easily. And then one last characteristic is that under Windows NT, you can have file names which are up to 256 characters long. So no longer are you going to have to struggle with file names that have an 8 characters followed by a 3-character extension. I'm sure a lot of you out there have struggled with trying to come up with unique yet meaningful names with that very small number of characters available to work with. So now you have up to 256 characters which you can use. And again, I want to show you during the next demonstration how that works with the existing FAT file system and how, in fact, you can pass those longer file names over to DOS and back again, and what the implications of that are. Some other of the advantages of NTFS, again, include greater security, where users can specify who can read and modify files, who can list particular directories, or who can add files to a directory. Again, nothing that's not pretty familiar to people coming from either a VMS or a Unix background. The type of security is called discretionary access control because, again, it's up to the user or the system manager to determine who has that access. As I have indicated in the earlier presentation, in future releases of Windows NT, there may also be support for mandatory access control where security has to be set up on not just files and directories, but other things as well. The other advantage which we talked about earlier was the support for the advanced fault tolerance, where you basically keep a transaction log to keep track of all changes and can use this log to bring up the system very quickly with no disk pointer problems in case there's something like an abnormal system shutdown of some kind. One point about this is that it's uncertain yet whether the logging capability will be there with the first release of Windows NT. We should know a lot better when the next beta version of NT becomes available in the next month or so. Now, there are also some possible disadvantages of NTFS, although I would call them really, I think, more inconveniences than actual disadvantages. NTFS is only recognized by Windows NT, which means that if you boot up under DOS, let's say from a floppy disk, there's no way at the present time which you can access files on that NTFS partition. Or if you're using the Flex Boot option, you might have a FAT file partition for C, but an NTFS file partition for a D partition. Again, if you boot up under DOS, you will not be able to access that NTFS partition. One of the things, again, that hasn't been too well defined so far is how we're going to be able to recover NT if you do have some sort of a disk problem. As you may know, if you're familiar with DOS, you always carry around a bootable DOS floppy, so you can boot up under that if your DOS system can't reboot. As part of the Windows NT installation process, you go through and it loads everything off of the CD-ROM, and then it asks you to insert a floppy disk, which it writes something to, and then you're asked to label that disk file system crash recovery disk. But the documentation never really tells you what to do with that. So I'm hoping that in the next release again, they're going to tell us a little bit more about how we can recover from those type of disk errors. They're certainly not doing that at this point. So again, that's something you have to be aware of. One other point about NTFS versus FAT. I've found from my own personal experience that I like to have a primary partition that's a FAT partition. And what I've done on my system is I've loaded DOS and Windows 3.1 there, as well as my Windows NT operating system. And then I have a separate partition, a D partition, which is designed to work around NTFS. And I like that because it allows me to do experimenting back and forth, but still gives me the ability to recover from any type of a system crash. At least I can recover from a DOS crash. And I can also continue to use the DOS operating system when I have to in all of those applications. So that gives me the most amount of flexibility at this point. The other thing is that even in the documentation, they'll warn you that NTFS is not fully debugged at this point, so there could be possible problems. So we've talked a lot about the NT file system, which is certainly, I think, one of the major components of the I/O system. The I/O system itself is designed much the way Windows NT itself is, where more generic routines exist on a higher level, and then down at a lower level, you have things which are more hardware specific. So the I/O system under Windows NT really consists of 4 different layers, I would say. The first one is the I/O manager, which contains very generic file I/O routines, such as read file, write file, open file, and so forth, and really exists independent of any particular file system, such as NTFS or FAT. Then what the file system is going to do is look at the file specification, see what partition you specified, and call in the appropriate file system drivers, whether they be NTFS, FAT, etc. Then at yet a lower level, you have the intermediate device drivers, which are code for doing various I/O processing. And then at the lowest level, you have the NT executive device drivers, and these are responsible for actually going out and communicating with a particular physical device. Moving down into the lowest level of the operating system, we have the Windows NT kernel. The kernel is responsible for a lot of things, although not nearly as many things as many other operating systems kernels are, especially comparing it to something like Unix. Because remember, a lot of the capabilities which formerly exists in which might exist in a kernel on another operating system have been moved up into those integral subsystems, or even up higher into the environmental subsystems. So the kernel now has several things which it's primarily responsible for. Certainly one of those things is to handle information from the hardware. So it's responsible for responding to interrupts and exceptions. And this is an area where the kernel really bypasses the HAL layer, which we'll be talking about next, the hardware abstraction layer, and has to talk directly to the hardware itself. So this part of the kernel contains very machine-specific code. You have the scheduler, which is responsible for scheduling threads for execution. Remember, every application consists of at least one process. That process contains at least one thread and possibly multiple threads. And again, Windows NT, the scheduler works on a thread-by-thread rather than a process-by-process basis. The kernel is responsible for synchronizing the activities of multiple processors, because when you have a multiprocessing system, you have various locks which have to be applied at certain times. You have various resources which are being shared, such as memory, and it's responsible for the kernel, it's the responsibility of the kernel to orchestrate all of that. Finally, you have the job of the kernel being to implement and supply various low-level objects, again, working with the object manager. We talked before that there were 2 classes of objects, both an executive class object and kernel class objects. And then right above the hardware layer, you have the hardware abstraction layer. This, again, is the key to the portability of the Windows NT operating system. Actually, there are probably 2 keys. One is the fact that the operating system was written primarily in C. The other one is all the machine-dependent code, or most of it, has been moved into this layer of code. We discussed the HAL layer a little bit yesterday when looking at the port of the Windows NT over to Alpha. But just to review, or for those of you who weren't there for that, it exists as a level of code between the executive or the integral services, integral subsystems and the hardware platform itself. There's different HAL code for every different hardware architecture. So the Intel platform has one unique HAL code, the MIPS platform has another, and the Alpha platform has its own HAL code. And again, this was the major, where the major amount of the work went into porting Windows NT over to Alpha, was in rewriting that HAL code to take advantage of all the features of the Alpha AXP architecture. It's also, again, the job of the HAL layer to hide as much hardware-dependent information as possible. This is part of what makes device drivers relatively portable under Windows NT, because as long as the device driver can go through the HAL layer, it can remain the same from one platform to another. There are times, though, when you don't want to go through the HAL layer. There are times, as I mentioned before, where the kernel doesn't. There are also times when, for purposes of speed, especially in the design of device drivers, you may want that device driver to talk directly to the hardware, bypassing HAL. That's fine, but the cost is you lose a level of portability that you might otherwise achieve. So the device driver designer, just like the kernel designer, has to decide, do they want to optimize for performance, or do they want to go after the greater portability instead? Okay, we've looked at the major components of the operating system. And what I'd like to do is change the focus a little bit now and talk about some of the system administration functions that you get with Windows NT. We're going to have a demonstration coming up very soon which will show you these functions so that I don't have to just talk about them here today. But one of the main things about Windows NT right now is that system administration is done through the same graphical user interface as everything else, which means that system administration is fairly intuitive. In fact, right now, there is no system administration documentation. I'm hoping this will be cured for the next beta release of Windows NT. But everything that I'll be showing you in that demonstration is really things that I've been able to figure out fairly easily because of that user-friendly graphical user interface that's presented. Some of the functions, system administration functions that you're able to perform under NT include creating and managing user accounts, performing security functions such as setting up security on files and directories and setting up user rights, managing your files and printers, although that's actually done, a lot of that is done through the file manager application instead of the system administration tools specifically. There's applications which allow you to do backup and restore in a fairly straightforward manner. Tools to allow you to manage performance and monitor performance, and managing servers and disk resources. So what we're going to do now is we're going to have another demonstration, and in this we're going to look at Windows NT from a system administrator's perspective. So we'll look at a set of administrative tools, including the user manager, the disk manager, the performance monitor, backup, and the event viewer. So let's turn now to the demonstration of NT from that system administrator's point of view. In order to demonstrate the system administration utilities which come with Windows NT, I'm going to log in as the administrator. So the first thing I need to do is change the username to administrator. Now the administrator under Windows NT is a lot like the system account under VMS or the root account under Unix. The user interface will look a lot like what we've seen already. However, there are certain things which an administrator can do that a user can't. Now, one of the things you'll see displayed right here is a message which says my password is going to expire in 7 days. I won't change it now, but I'll show you how you can modify the expiration date as one of the things which you'll see in this next set of demonstrations. Okay, for the purposes of this demonstration, what we'll do is we'll open up the icon down at the bottom called Administrative Tools. And in there we see 5 different applications. The User Manager for creating, modifying, and deleting user accounts. The Disk Manager for setting up your disks, configuring your disks, and getting information about the status of them. Performance Monitor to monitor the performance of various resources on your system. The Backup Utility for doing backups from disk to tape and restoring from tape to disk. And finally, the Event Viewer which allows you to keep track of various activities which are occurring on your system. Let's begin with the User Manager. In this window, we see displayed up in the top window all of the accounts which currently exist on this system. I have an administrator, I have a guest account, and I have an account named Wise. In addition, down at the bottom are various groups. These happen to be groups which are predefined by Windows NT. In addition, you can create other groups. Each group has certain sets of privileges or rights which are associated with them. Why don't we start out by creating a new user account on the system? And I'm going to do all of this through the graphical user interface rather than through command line typing like I would under most systems. I will, under the user menu, I'll select New User. And in here I would type the name they type into the system in the logon box. I'll just create one called Demo. Tab down to the next box and we'll call it Mr. John Demo. And we'll just say that this is a demonstration account. In addition, I could define a password right now, or I can say that they have to create a password when they log into the system. Down below here, we can specify that the user must change the password or not. The user cannot change the password. This might be useful for something like a guest account, where many different people are using this account at different times. We can select the option Password Never Expires, which is something that you don't want to do usually for security reasons, but if you forget your password all the time, well, maybe you do want to do it. And finally, you could create disabled accounts. This might be useful if you know that there are going to be 20 new users coming into your workplace a week from now and you want to set up their accounts ahead of time. In addition, we have two buttons down here, one to specify the groups that our new account is a member of, and also a profile which sets up their user environment. Let's start by looking at groups. We can see that the user is a member, Demo is a member of the users group, which again has certain privileges associated with it. I decide perhaps that I don't want this person to be a member of the demo of the users group, so I can select users and remove that from the list of groups which Demo is a member of. Maybe instead I want this user to be a guest, which has very limited privileges associated with it, so I'll select guests and then select add. And perhaps I want this new user to be able to do backups of system files, so I'll make him a member of the backup operators group and add that as well. In addition, under profile, I can set up various parameters for this user. For example, I can have a specific logon script being executed. A logon script in Windows NT is a batch file. This batch file can contain various commands which get executed. As an example, I might want to start up certain applications, or I might want to modify certain environmental parameters. So again, what I would do is just type in the name of a particular login script. In addition, I can specify a specific home directory for this person to log into. It can either be on the local system, and I could make it something like defaults/demo, or if I have a network environment, I can have this person automatically log into a directory which actually sits out on a remote system somewhere. With all of this set up, I can now say OK, and it's now writing all of this information out to a database on the system where all user accounts are listed. And now in our display of users, we can see that our demo account has in fact been added. Some of the other things that we can do with this application is set various policies. For example, account policies. I can set it up so that passwords never expire if I want to. Or I can say that they expire in 90 days, or I can modify that amount to some other value. I can say that there's a minimum password age. In other words, people either have to change their password immediately once they log on for the first time, or that they can make changes after so many days. I can specify a minimum password length, and I can also specify password uniqueness. In other words, if I make the person create a new password, do I want them to use passwords that they previously used? I can specify how many old passwords I want them to remember. So you can see that the Windows NT User Manager has a lot of the same sophisticated features that you see in operating systems such as VMS. I can also look at user rights. This is where I set up the various group privileges. And if I select this item, we can see the types of rights that different users can have. For example, I can allow a person to back up files and directories. I can set it up so that they can create a page file or debug programs. Let's go down and look at some more of these. We can have people who are allowed to log on to the local system or load and unload device drivers. And further down, we can see that some people may be able to shut the system down while others can't. And finally, we have auditing, which allows you to audit various things that users are doing, such as logging on and logging off to from the system, shutting the system down, making use of the user rights, and changing various file and printer and security setups. I have it right now so that we're actively auditing logging on and logging off. Now you might say, how do I look at those various events, log on and log offs on the system? Well, to show you that, let me exit from the User Manager program and turn for a second to the Event Viewer. In the Event Viewer, we can see that right now we're viewing all of the different logons and logoffs of user Ys, and we can see whether they're successful or not. If I want to, I can get a look at all of the users on the system. So let me first of all select Filter. And from here, I can say I don't want to just look at Ys, I want to look at all users. We'll now select OK. And now we can see that besides Ys logging in, we've had the administrator, we've had guest, we've had others as well. The Disk Manager allows us to look at how our disks are being used and how they're configured. When I start this up, I can see that we have a single hard disk on our system. It's 203 megabytes in size. And it's been divided up into several partitions. The first one is the C partition. This has a label of MS-DOS 5 and is a FAT file system. FAT, remember, stands for File Allocation Table and is the file system which MS-DOS uses. This is also 100 megabytes in size, and I can tell by the stripe of color on the top that if I go to the color key down here, it's a primary partition. The D drive is a logical partition. I can tell that by the slightly different shade of blue. It also indicates here in the display that it's an NT file system, and it's 60 megabytes in size. And finally, over on the right-hand side, I have some free space for 43 megabytes, which I could use in the future to create additional FAT, HPFS, or NTFS partitions. In fact, to show you at least how you would start doing that, I can go to the Partition menu and select Create. Now it's going to give me a warning that if I do produce a new partition, it may be incompatible with DOS. But I'm going to say, yes, I want to continue anyway. At this point, it would now allow me to define what size I want to create my partition. So it can be 43 megabytes, or it can be less than that. Once I've defined the size of my partition, then what I would have to do is I would have to exit this application, go to the DOS prompt, and use the format command in order to format my disk. From there, I could then, and during that formatting, I would specify which file system type I want to use. At that point, then I could start writing data to that new partition. Now, right now, because I only have a single disk, I don't have many items selectable in this menu. Most of them are grayed out. But let me just give you a brief run-through of what each of these says so that you can get an idea of what you could possibly do with a system that has more than just a single hard disk. We talked earlier about how Windows NT has features which support file system and disk fault tolerance, technologies that are very similar to what you see with the RAID technology. And if we go through here, we can see that besides deleting our partition, we can create a volume set, we can delete a volume set, we can create a stripe set. Remember that a stripe set is where you have the contents of a single partition split up over several disk drives. We can delete a stripe set. We can mark a partition active. We can change the drive letter of our partition. And the configuration simply allows me to save or restore various information about a particular partition. Finally, up in the next menu, fault tolerance. Again, none of this is active because we only have a single drive. But if I had more than one drive, I could establish a mirror or break a mirror, or I could create a stripe set with parity or delete a stripe set with parity. And finally, if I lost one of the disks within my stripe set, I could regenerate that data using this utility. That concludes a look at the Disk Manager utility. The Performance Monitor is used, as you might imagine, to view various types of performance of various resources on the system. To get an idea of what those resources are, let me start up the Performance Monitor, and I'm going to go to the Edit menu. And what I'm going to do is I'm going to create a chart. A chart simply charts various performance parameters. I would select Add to Chart, and a dialog box appears which allows me to establish the monitoring. Now there's a box down here which is Object. If I want to look at what those objects are, we can see that they include various net buoy resources having to do with networking. We can monitor objects, the physical disk, process or processors, redirectors, servers, systems, and threads. In addition, I have an instance box to the right of that. This would be used in a multiprocessor environment where I could monitor resources on a variety of processors on that single system. I'm going to stick with the default resource, which is processor. Now, within that processor, we have various types of counters. And the first counter I want to monitor is the amount of time the system spends running in user mode or non-privileged mode. So I'll select user time. I'll make the display a red line. And in order to increase the visibility of it, I'll make the width somewhat larger. Once I've set up all those parameters, then I can add that to the chart. Next, I'll select privilege time. This is the amount of time the system runs in privilege mode on the system. By the way, if I want to find out more about each of these values, I can go over to the right-hand side and select Explain. And down at the bottom, we'll have a display of what each of those counters means. So again, I'll select privilege time. I'll say that I want the color to be in green, and we'll simply add that to the chart. we'll look at total processor time, and we'll make that blue. And finally, I want to monitor interrupts per second. And because I sometimes find yellow difficult to look at on the screen, I will select a different color from my chart here, and we'll make this one a dark red. And again, add that to the chart. Once I'm done, now I can look at all of those different values. Down at the bottom, in case you couldn't remember what each one stood for, we have an explanation. Notice that one of my values, the interrupts per second, goes right off the top of the chart whenever I move the mouse. That's because mouse movement, along with such things as keyboard movement and disk I/O, generates system interrupts. So every time I move the mouse, the interrupts go right off the chart. If I wanted to find the maximum value of that, what I would have to do is change the range of numbers over on the left-hand side from 0 to 100 to some higher value, because I'm generating more than 100 interrupts per second. So let me go to Options, and I'll modify the chart options, and we'll set a vertical maximum of 300. Select OK. And now we can see that, in fact, it is 300 is the maximum value. And now no matter how much I move the mouse around, the value never goes up above the top value of the screen. Besides that, I can modify many other display factors as well. Let me just show you one of those, which is to generate a histogram rather than a graph. And you can see that that's a very different type of a display. In addition to simply monitoring things on the system actively like this, you can also choose to log all of these values to a log file somewhere, and then either print them out later or view them using the event viewer, which we saw a second ago. Finally, when I'm done setting up a chart the way I want, I don't have to go and repeat this every other time I want to look at the same chart. What I can do is I can save chart settings to a file if I want to. And finally, when I'm done, I can exit from this application. The final application we'll look at is the backup utility. Unfortunately, I'm not going to be able to show you very much because I really need a tape drive hooked up to my system in order to do this. But let me show you what the user interface looks like. I start by getting a warning which says, no drive has been detected, referring to a tape drive. I know this, and I'll select OK. The way that the application works, though, is you can either select an entire disk partition, or you can select parts of a disk partition. For example, I might select a group of directories in the root directory. And from here, I could then drag these selections down to the tape drive and have my backup begin. Or I could select backup from the button at the top here. In addition to backup, I can do a restore, which moves data from the tapes back onto the disk. I can create catalogs or listings of the files and directories which I've backed up. I can erase a tape or eject a tape. And if I did have a tape drive on my system, I could configure that. Finally, I'd like to conclude the demonstration of the administrative tools by revisiting the event viewer. As I indicated earlier, this can be used to monitor such things as security events. For example, people logging on or logging off the system, or changing rights and privileges on the system. The way you specify what you want to be displayed here is through the log menu. So I can log system events, security events, or application events. Now, I actually set up the logging for each of these from different applications. For example, the security logging is actually specified in the user manager utility. In addition to that, I can open up various log files, save various log files, and clear all events. Like with most logging systems, you want to be careful about how many events you're actually logging, because if you log too many or don't clean it up, you can fill up the disk in fairly short order. However, in most of the setup of most of this logging, you can also say you want the logging to stop if the disk gets near full. As we saw earlier, besides looking at all events, I can also filter events so that I only get certain types of events being displayed. I can specify a range of time. I can also specify that I only want, for example, certain users being modified or certain computers if I'm on a network. And I can specify that I want the newest events displayed first or the oldest events displayed first. And I can do a search for a particular event category or event ID or user or so forth. That concludes our look at the event viewer, as well as our look at the administrative tools which come with Windows NT.